dear student. This is Devang Shah from LG Institute of Engineering and Technology under the LG University. Now, during our last session, we have discussed about the logic gates that we built from the help of diode, resistor and transistor. To carry forward this again, we have to understand a different kind of logic families. So what are these logic families? Logic families are nothing but here we are using different kind of components or electronic components like diode, resistors, capacitors, inductors, transistors in a circuit to realize a specific kind of logic gates, right? So we start with further, we have to realize a kind of logic families. Right. So we'll start with the concept of logic families. You can see the logic where it categorized into two parts. One is called standard logic and another one is called ASIC logic. This is called the application specific integrated circuit. Right. From that ASIC we have a different kinds of families like PLDs. That's what we are going to learn today. We are going to discuss today. Gate arrays, cell based ICs and full custom ICs. Based on PLDs we have SPLD, CTLD, FPGAs. We are not much going into that high-tech technologies, but in PLDs, we are going to discuss about the kind of ROM, EEPROM, EEROM, then we are going to discuss about PLA and PAL, right? Based on that, if we further discuss about the kind of logic families where we define a kind of different logics, we can implement using those kind of terminology where one of the logic family type is called RTL, which is called a resistor transistor logic. Now what does it mean? Here there are certain stages. The first stage we are using resistor, another stage we are using transistor as a switch. Based on connection of resistor and transistor, we can realize the logic family as RTL, resistor transistor logic. Likewise, we will also discuss like DTL, which is called a diode transistor logic, that is in circuitry. The diode and transistors are connected in such a way that we can realize a specific kind of logic gates, right? Same way TTL is a transistor logic. Then you have ECL, which is called emitter coupled logic. Then you have a MOS, which is called a metal oxide semiconductor logic. And lastly, it's a CMOS. So normally in our syllabus we have covered a CMOS, which is called a complementary metal oxide semiconductor logic, right? So based on that, we are going to realize the different kinds of logic gates like basic logic gates, universal logic gates, exclusive logic gates you can design with the help of either RTL, DTL, TTL, ECL and CMOS, right? So we'll first start with what is positive and negative logic. So we already know the positive logic, that means 0 is set as a binary 1. Positive logic is nothing but a kind of high logic where H or binary 1 is taken as a logic 1, right? Same way in negative logic, that means here the plus 0 volt we take as a binary logic 1. So what does it mean? Logic, a positive logic, that means plus 5 volt will take at a logic high, that means binary 1. Same way the negative logic, that means here 0 volt will take as binary 1, right? So based on that, if we take the input and output is this positive logic NAND gate, you can see if both the input is low, your output is high. This is based on the positive logic. So X and Y, if both are 0, 0, way you can take it like that way. If both are 0, 0, see the output goes to 1, right? So you already aware about this particular logic gate, the truth table of this logic gate. So based on that positive and negative logic, see we can define. We are just changing the the representation of our input. In some of the circuitry we take 1 as a plus 5 volt. In some of the circuit we take 1 as a plus 0 volt, like that. So there are certain different features of the logic families, or we can understand as a parameter. In our previous session we also discussed what is a fan out. Fan out is nothing but number of standard loads can be connected to output of the gate without dragging its normal operations. Sometimes the term we can consider as a loading. What is power dissipation? The power needed by the gate to operate in a milliwatt form. Propagation delay is like average transition delay time for the signal to propagate from input to output when the binary signal changes its value. Noise margin, the unwanted signals are referred as a noise, and noise margin is nothing but the maximum noise added to the input signal of a digital circuit that does not cause undesired change in an output of that digital circuit. So what is computing it a fan out in a high level condition? You can see in this particular gate, see, there is a NAND gate. After output of NAND gate, there are two more NAND gates are connected. So I can consider here the fan out condition is 2. So that means this particular output of the first NAND gate can be able to drive two more NAND gates, or two, because this output of the NAND gate is applied to two more NAND gates as an input. So it can able to drive two more NAND gates. That is called the fan out condition. Same for this case, it's a low level, so we can just representation is part of the 1 and 0. This is nothing but the fan out condition is 2 here. Same way the features of BJT, if we consider the BJT we are taking as a part of the switching element. So here you can see that this is a kind of inverter circuitry where RB is connected to the base of the transistor, emitter is connected to ground, and you are taking your output from the collector terminal. See, once you apply VI as a 0, that means this particular transistor is off, so switch is open, and if this switch is open, VO goes to plus VCC. That means if you apply 0, VO goes to VCC, that means your output is 1, right? And likewise, if Vi is equal to 1, see the base of the transistor is 1, that means switch is closed, that means VO is directly connected to ground line, like that way. The VO is directly connected to ground line when transistor would act as a closed switch, right? So VO goes to 0. So this is what is nothing but the realization of inverter. So this particular transistor you can make from NPN, PNP, we all know that it is made up from the semiconductor material silicon and germanium, and most popular is NPN. Based on that, you can realize this kind of NOT gate by making this kind of inverter circuit with the help of resistors and transistors. So this is a one kind of family where you can put resistor and transistor all together. So this is one more term where here we have taken all those transistors in a parallel with each other to realize the NOR gate, right? So it's simply logic is nothing but a kind of inverter logic, but since you are putting all these switching components as part of the parallel, see you can realize the kind of NOR gate. So once all the inputs is here, we have taken the truth table of the two inputs, but you take all these three inputs are 0 0 0. See, so here you can realize three transistors are connected in parallel with each other. So if A, B, C all are 0 0 0, see the transistor would be off, so would act as an open switch, and your Y becomes 1, right? Because Y is directly taking output from VCC, so it's a 3.6 volt, right? So again, if all the inputs are 1 1 1, see any one of the transistor is on, and that would connect it to ground line, so your output goes to 0, right? This is what the logic of NOR gate, but you have realized with the help of resistors and transistors, right? Again, once we talk about the diode transistor logic DTL, the same kind of logic you can see the diodes are connected parallelly with each other. It's A, B and C. So there are three inputs of A, B and C, and you can realize a kind of NAND gate at the end of at the collector of the transistors, where you can see A, B and C, these are connected, and that would generate a kind of AND gate. So here the initial part of this the circuit with connection with the three inputs A, B and C with the diode. So this particular portion would act as an AND gate, and after that you have just connected the inverter. So it's a NOT gate. So AND plus NOT, you have realized the kind of NAND gate, right? So here A, B and C, all these three inputs are 0. So here the input of the transistor becomes 0. It's connected to ground. Once it is connected to ground, the Q1 transistor is off. That means switch is open. If the switch is open, see the output Y goes to 1, right? If all these inputs are 0 0 0. At the extreme condition, if all these three inputs are 1 1 1, what happens? If all the inputs are 1 1 1, again, see your output, what you have plus 5 volt. So plus 5 volt of these three diodes, that plus 5 volt is applied to the transistor Q1, and transistor Q1 goes on, and if it goes on, it would act as a closed switch. So Y is here directly connected to ground, so your Y becomes 0. So this is nothing but the implication of NAND gate. So by that way you can realize the truth table of NAND gates, right? Based on that, further modified you can DTL and making more low power dissipation circuit by putting just the Q1 in between. So in that case, again the logic would be same, and that again you can realize a kind of NAND gate where you are going to connect ABC. Again, if you are taking ABC all zeros, so output goes to 1. So Y is connected to plus 5 volt VCC, and once you apply ABC, all are 1 1 1. That means transistor Q2 goes on, that means it would act as a closed switch and Y goes to 0, right? So again you can realize the same NAND gate using this modified DTL gate, right? So I mean to say that here resistor transistors, it is diode transistor, again is a transistor logic. You can again realize a different kinds of logic gates, and you can construct a different kind of logic gates. You can see this original, basically this TTL gate was a slight improvement in DTL. So every time in some earlier days we have used RTL and DTL. Now is a case of DTL where the power consumption is very low, so the voltage requirement is also very low. In this condition you can have a less propagation delay, so your circuit must be very fast. So there are several TTL subfamilies of series TTL technologies available. Has a number start with 74, right? So we have a 74 series of ICs like 7404, 74 S86 and so on. There are 3 types of TTL configuration like open collector, totem pole connect output, and 3-state tri-state outputs. We are not much going into, we'll just check the kind of TTL circuitry where see that here the resistor is gone, diodes are gone, but at the input side the transistor itself will is connected. So here you can check the 2 input NAND gate where A and B all are connected with the emitter terminal of the transistor. When this 2 goes to 1, see your transistor TR2, right, goes on. When it goes on, that would act as a closed switch, and your output Y or output Q becomes 0, right? So available at a 0 ground. So the same terminology you can apply for this 3 input open collector TTL gate, and by that way you can realize the NAND gate using this transistor logic, and further you can consider this kind of wired AND and 2 open collectors. We just realize the kind of Y is equal to AB plus CD of whole bar by making this kind of so inside OC this is kind of using the TTL logic is like transistor logic, and you can realize this kind of Boolean functions through this. Same way with the TTL you can use a kind of totem pole output. This is one of the type of this TTL logic where you again the terminology is same where you have used transistor. So input as a transistor and output as a transistor, and you can realize again this kind of NAND gate using this TTL gate. Same way here you can also realize a kind of 3-state TTL gate where the circuitry you can see the kind of inverter gate is available where the transistor's data input is A is available, and at the Y you are going to have a kind of inverter state where it is having the 3-state where after that the Y goes to 1. So if you apply the input data is 0, right, and Y goes to 1. So this is a one more kind of terminology behind the TTL, and everything is again a kind of trade-off between the parameters, right? So again this particular logic you can also develop, and kind of circuit you can also design, and based on that you can again realize the kind of TTL logic. So now one of the logic is defined as emitter coupled logic, ECL, the non-saturated digital logic family, having the propagation delay is very low, 1 or 2 nanoseconds, very much high speed, and the requirement of voltage is very low. So here that will include a differential input amplifier, internal temperature and voltage compensator bias network, and emitter follower circuit. So based on that, if we further discuss about a kind of emitter coupled logic where you can see there are 4 total inputs A, B, C, D, and at the output you are having both the function like OR function as well as NOR output functions, right? So here you can realize a kind of emitter coupled logic where the emitter is coupled with a resistor and then connected with the input terminal. So here you can see here how the transistor and resistors are paired together, where the emitter terminal of the transistor is connected to the resistor, and in between terminal you have taken your input A, B, C, D. After that, so this is I'm just talking about this particular portion where you can see the resistors and transistors are connected together, where it will take the input supply as A, B, C, D, or it will take the input as A, B, C, D. After that, this particular terminology is like a emitter follower output, with this is directly give 1 or 0 or 0. So here
You can see this particular internal temperature and voltage compensated bias network would act as an inverter, and from that, see, you can be able to define a OR gate and a NOR gate both simultaneously. So this is what the symbol of OR gate and OR gate and NOR gate that can be realized using this ECL logic family. So again here the components are transistor, resistors, diode are connected in such a way that you can get a two important logic gate realization. One is OR and another one is NOR, right? So this is one more type, and the last one is a you can consider as a CMOS or a complementary metal oxide semiconductor family, where all this now logic is shifted to only and only transistors, and those transistors are now called NMOS or PMOS, right? So ultimately it's a metal oxide semiconductor transistors where diodes were gone, transistors were gone, and the BJT based transistors were gone, registers were gone, only and only the CMOS logic exclusively coming in the picture, where in CMOS contains the P channel metal oxide semiconductor, N channel metal oxide semiconductor, and we are taking, see, both as a complementary with each other. So one of the you can see the CMOS gate is a system consisting of PMOS pull-up network. So the upper portion is the PMOS and connected to the output one or VDD, and NMOS is a pull-down network. So the NMOS is connected to ground. You can see the complete this logic we define as a complementary metal oxide semiconductor because it's a network of PMOS and NMOS, right? So based on that particular fundamental inverter circuitry, you can see the upper portion as a PMOS and the lower portion as a NMOS. Once you apply zero, see, at one of the time any one of the transistor goes on, right? So if you apply zero, the upper transistor goes on, so it would act as a closed switch, and the down transistor which is a NMOS which goes off, it would act as a open switch, right? So from that, once we apply zero, since the PMOS is on, see, the output wise directly connected to VCC, and that will give you a logic 1, right? So this is nothing but a kind of realization of inverter gate or NOT gate using CMOS exclusively, right? So you can see this for more diodes. You can also realize like CMOS to input NAND gate and NOR gate, right? So the fundamental is same as it is. If you want to realize a kind of AND gate or OR gate, you just make the series and parallel combination of maybe it's a transistors, maybe it's a diode in case of DTL, transistors in case of RTL or TTL, and CMOS again in a case of PMOS and MOS in this configuration. So you can see here for CMOS to input NAND gate, see, one of this part is would act as an inverter, and since these two are connected in series with each other, and then you have an inverter, so these two are connected in a series, that would give you an AND gate. Any inverter will give you a NOT gate, so hence this is called the NAND function it will generate. Same way here, these two transistors are connected in parallel with each other, so both are in parallel, and this will generate a kind of complementary of this. So it's like again OR plus NOT gate, so that will give you a logic of NOR gate. By that way you can realize all the kinds of logic gates using the CMOS technology. So nowadays in all electronic chips that you can see in a computer motherboard like Intel chip, everything is again based on a CMOS transistor logic, or we can say a CMOS logic family, and so on, right? Dear students, some of the advantages of CMOS logic families, like input impedance is very high, so the noise margin it can, in very broad level, it's going to be controlled. CMOS logic uses a less power. That is one more important advantage. Power dissipation is negligible. Fan out condition is high, so it can drive more logic gates. TTL compatibility, stability of temperature is good. Noise margin is good. Compact, robust mechanically. What are the disadvantages? If you consider the cost would be increased once the processing steps increases, however it can be resolved. The packing density of CMOS is low compared to the NMOS. Another drawback of CMOS inverter is that it utilizes the two transistors as opposed to one NMOS. So that means if there are n number of PMOS you are going to use, same way n number of NMOS you have to use in a complementary metal oxide semiconductor, right? So this is what one of the drawback because the cost would be high. Application of CMOS is the computer memory, CPUs, microprocessor design, flash memory chip design used to design an application specific integrated circuit like ASICs. Right. Thank you, dear students. Here we learn about the different kind of logic families. You can design a different kind of logic gates. Thank you very much.